Good evening, my dear JEE warriors. Welcome aboard to the PWJ English channel. This is your Captain Shreyas, and we are in the backlog series. In the previous session, if you recollect, let me just show it to you.
Good evening, my dear JEE warriors. Welcome aboard to the PWJ English channel. This is your Captain.
Yeah. So in the previous session, if you remember, we had a backlog class couple of days back, and here we are. Yes, mechanics for class 12th, and I introduced the concept of vectors, the addition of vectors, and how to play along with, those concepts in your 12th standard electrostatics chapter, where we discussed Coulomb's law, in fact, multiple forces, which is indirectly superpositioning theorem, where you use vector addition and all of that for your concepts of electrostatics. So if you have not yet watched this particular class, my advice will be please watch this as soon as possible, because you will clear a lot of things from your 11th, the initial chapters for your chapter of electrostatics. Okay, all right, let these people get done with their fashion show so that I can actually show you my lecture and what I was talking about. All right, bro, so many ads. Okay, I'll learn Python and snakes and everything very soon. Hi, good evening. Hi, Azad. Good evening, good evening, good evening. So you can see right over here in this particular lecture, it's a very detailed class. We have talked about, vectors, additions, and we have used it in Coulomb's law and so many other things, so many other things. Okay, so please check that lecture out. It's a very important thing. We have also discussed majority of Newton laws concepts also in this particular chapter. Okay, now what are we going to do today, you might be asking. So in today's lecture, we will be focusing more on the energy aspects, the potential energy, and then I will try and relate that with the force concept, because that is one of the most difficult concepts in that entire chapter. And then we can also talk about the concept of field and potential, which is the main thing throughout the chapter. And then we can probably discuss other things, maybe like a little bit of dipoles and other stuff as well. Okay, so let's begin with the class. I hope you guys are ready. All right, so today Azad is a more of a backlog class. I wouldn't say this is like the entire chapter, but it gives you a head start so that you can watch a complete lecture in a way. Okay, otherwise it becomes difficult. Hi Saundar. Hello Sri. Sir, can I watch this lecture without watching that lecture? Saundar, I feel you might get left out a little bit at times, but if you know at least basics of vectors and Coulomb's force, I think you can watch this lecture. Okay, I hope you have answered your question. Okay, if you know basics of vectors and if you are aware with Coulomb's law for electrostatics, that is good enough. Hi Shimeen, good evening everyone. So let's begin with the lecture. Now, just to do a quick recap, we had said that if you have two charges, Q1 and Q2, and they are separated by some distance r between them, then there is a force of attraction or repulsion, and that particular force is given by, first of all, there is a constant 1 by 4 pi epsilon naught, which is called as your Coulomb constant, whose value is 9 into 10 to the power 9 Newton meter square per Coulomb square, right? This is your SI unit, multiplied by charge 1 into charge 2, that is the product of the charges, and here you have R square. This is called as your Coulomb's force, and this is also called as the Coulomb's law. And because there is a square of the distance in the denominator, it is also called as the inverse square law. Like the law of gravitation is also an inverse square law, because the gravitational attraction is dependent inversely to the square of the distance. Even magnetic force is an inverse square law. But you will learn later in the 12th standard chapters of nucleus that the nuclear force is not an inverse square law. So if you are wondering, is there any force which is not inverse square? The answer is yes, and that is nuclear force. But for now, gravity, electric, magnetic forces, these follow inverse relationship to the distance square. Now using this concept, we were able to figure out the forces between any two charges, and we saw that if both the charges are positive or both the charges are negative, then I said that it would be repulsive in nature. But if one is positive, other is negative, then we saw that it was attractive in nature. This was attractive in nature. All right, great. Okay, this is standard. Everybody fine till this point? Can we go ahead? Hi, study with Meta. Good evening. All right. Hi, Deep. Good evening. क्वांटम गेम मेरे को बहुत अच्छी हिंदी आती है ना. मैं महाराष्ट्र चैनल पर भी प्रॉपरली हिंदी में ही पढ़ाता हूँ, पर ये इंग्लिश चैनल है तो इसलिए हम यहाँ पर इंग्लिश में ही बात करेंगे. राइट? ओके, ग्रेट. So good evening everyone. Yo, amazing soundbar. So if you know the basics, today's lecture will be a breeze then of Coulomb's law. So anyways, I have revised this. Now that we understand the concept of force between two charges, I feel that this force is going to give rise to some kind of energy. And before I talk about that energy, let's understand this nature of the force. And this Coulomb's force, this particular Coulomb's force is a conservative force, is conservative in nature. After that, we can talk about anything else, which is the energy aspect. Now, what is the meaning of this word conservative in nature? The true meaning of being conservative in nature is that the work done by this force in a closed path must be zero. The meaning of the word conservative is that the work done in a closed path is always going to be zero. There is not even one single path where it is not zero. So it is always going to be zero. Now going back to what was work. Work, if you remember, work is nothing but the transfer of energy. All right, transfer of energy from a body to another via a force. So for example, if I have some box over here and somebody is applying some kind of a force over here, F, and as a result of which this box ends up displacing by an amount of S. So I am applying this force. So I am a body. I have applied this force on this box. So that is another body. I have transferred my energy to this box. I would have eaten. So today Shreyas Sir ate masala dosa. Shreyas Sir ate masala dosa. So it got digested. I got some energy stored in my body. So that masala dosa energy went into this box. So there is a transfer of energy because of the force. Without that force, it would never be transferred. I cannot just use mind control. Hey box, come on, you move. And I do abracadabra and the box starts moving. That doesn't happen. Okay, so and it cannot think on its own. And box is like, okay, Shreyas Sir is here, let me move. It can't do that. So you need that force for it to get that energy and be transferred. So that is what this means. And the formal definition of work goes like this. The work is nothing but your force vector dot producted with the displacement. Dot producted with the displacement. That dot is nothing but cos theta. That dot is nothing but cos theta. So simply put, it is the magnitude of the force into cos theta multiplied by displacement. So we all know that work is a scalar entity. Work is a scalar entity whose unit is nothing but a joule, which is nothing but a Newton into meter, a Newton into meter. So this angle also matters, whatever is there between the force as well as the displacement. This is the formal definition of work. Now, if by chance our force is not constant, then I cannot use this particular relationship. See, if I tell you, example sake, there is a electric force of maybe 20 I cap minus 2 J cap Newton on a charge that moves, let's say 3 I cap plus 4 J cap meters. Find the work done. Now here force is given, displacement is given. We have been asked what is the work done. So straightforward we can say that okay, this force is not changing, it is a constant force. You can see these numbers are constant. The displacement is also clearly mentioned. So I can directly use the concept of dot product. And I can say work is force dot displacement. My force is 20 I cap minus 2 J cap dot producted with 3 I cap plus 4 J cap. So using the rules of dot product, we know what to do. I cap multiplies with I cap, J cap multiplies with J cap. So 20 I cap into 3 I cap, 20 into 3 is nothing but 60. Minus 2 into plus 4 is minus 8. So this will be nothing but 52 joules of work. So this is nothing but 52 joules of work has been done by the electric force. Very straightforward. Okay. All right. No problem, Revati, Satya, I am here. Watch me over here. Okay. All right. Okay. So our motivation, any doubt, please ask me. But otherwise, yes, we can continue. All right. Now, if this force was not constant, if this particular force was not constant, then we cannot use this relationship, and then we are forced to use another relationship. So for a variable force, I can say for a variable force and even for a curved path, you can use this. Meaning, imagine I have this object, but that object is not going along a straight line. The object is going along some random curved path. So this is the path taken by it. And at each instant, the force acting on it is also not constant. It is changing, maybe direction, maybe magnitude, God knows, even both. So this angle might not be constant. Even the displacement vector might not be constant. So what you do is take up small displacements, ds, and you calculate the small work. So the small work done will be dw, and that dw will be nothing but the dot product of this particular force with this small displacement. So I move a very small displacement, maybe I do some 0.0005 joules. Then I move the next displacement, may I do 0.0067 joules. I keep on moving and I keep doing small joules. So in this entire path, I will add up all these small work done to get the net or the total work done. So I will say then the total work W is integration of dW from my initial to the final location. So my total work done will be integral from initial to final of the force with the displacement dot product, F ds integration. Is that right, everyone? Everybody with me on this? Yeah, this is how the logic is. Okay. Now that it is clear, okay, I need to do integration, meaning I need to add up all the small work done. So what if the force is given to me? Example like this. Say the electric force in a region is given to me as, let's say, x I cap plus y square j cap. Okay, it's given to me, and it is also mentioned to me that, hey, listen, this is how you're taking that particle, this is how you're taking that charge. You're first moving that charge here like this, and then you're moving it over here. So this is how you have moved it, like this and then like this, and you have finally reached the coordinates 2, 3. Okay, this is your x-axis, this is your origin, this is y-axis. Can you now find the work done? Can you now find the work which has been done? Okay, let's try and understand. This electric force for some reason is dependent on the x coordinate as well as the y coordinate. You don't have to break your head over it. It's given, so take it for granted. And now you are moving the particle like this, and then you have taken it here. You are required to figure out what is the work done in this process. Shall we do this problem? It's a very interesting problem. Okay. So, does the angle change at all times? Not necessarily in the variable thing. It might not change. Maybe the particle is going in a straight line. Maybe the force is at an angle. Maybe only the force is changing in magnitude, but angle is constant. That is also possible. Maybe force is constant in magnitude, but angle is changing. Or maybe force is constant and the particle is going like this here and there. So displacement might be changing direction. So any of them change, anything varies, either displacement, angle or the force, then you have to use integration. That is the point. Okay. When all three are constants, then you can simply do the dot product and just multiply force and displacement and cos theta and you get the answer, or just do the dot product. Simple. Is that okay? I hope I have answered your doubt, my dear. Yeah. Okay. Thank you, Baludam. Thank you. Okay. Now let's do this. First of all, let's see how am I moving. I am moving first here and then I am going here. So let's consider only for now this particular path. Now in this particular path, I am moving along the x-axis. So in this path, can you guess what coordinate is going to be 0 and what coordinate is not going to be 0? If I am going on the x-axis, it's obvious that the y coordinate will be 0 and it is the x coordinate which changes from 0 to 2. Y is equal to 0. That is basically the same. It is not changing. It is the x coordinate which is changing. So my force in that particular region, because my y coordinate is 0, will be simply x I cap, and there will be no y square only over here, or it will be 0 square j cap. It's as good as saying it's just x I cap. So you don't have to worry about j cap at all. You just have to worry about x I cap. Okay, great. Now the force is along x-axis. As you can see, I cap is there, and I'm moving also along x-axis, so work might be done. So in this particular region, the work done in this particular region from here to here, I will call this region number 1. The work done will be integration. This is a variable force because it is dependent on x. So F dot displacement. Here force is nothing but x I cap. What is my displacement going to be? Well, my displacement is dx. Everything is on the x-axis, so it will be nothing but dx I cap. Do you guys get it? Why it is not dy or dz? It is only dx because I am going only along the x-axis. Now I cap into I cap is 1, so hence this will just become integration of x dx, and I know the limits. X is varying from 0 to 2, so I'll just put the lower limit here and the upper limit over here. So integration of x is nothing but x square by 2. Limits are 0 and 2, lower and upper. So put 2 square divided by 2 minus 0 square by 2. So this is anyways going to vanish. So this is just going to become 2 joules. Is this fine? The first work is nothing but just 2 joules. Everybody till this point clear? Okay. Now what is the next thing? I will now continue my journey. Yeah, do not forget we have to reach our final destination, not the movie. Okay, so we call this path 2. Now in this particular path, can you guess what is same, what is 0, what is not 0, etc. I feel it is the x coordinate which is not changing. So x coordinate is 2, which is always going to be the same. But it is the y coordinate which changes from 0 to 3. Alright, perfect. Now if you write down the force in this particular path, my x coordinate is always constant. So it is 2i cap plus y square. Y square is changing. So I'll just put y square j cap. So if I write the work done in this particular location from here to here in this path 2, F dot displacement, so F bar dot displacement, observe this, my force is 2i cap plus y square j cap, alright, dot product with displacement. My displacement is happening in the y direction, so ds is dy, not dx, not dz, only dy, because I am going vertically up, so it will be dy j cap. Is that right, everybody? Why this is dy and why this was earlier dx, because you are going horizontally. So we know how this multiplies. I cap will not multiply with j cap. In fact, the multiplication will be 0. So it's only j cap that will multiply with j cap, and we will be having y square into dy. So we'll just be having y square multiplied by dy, and I know the limits of y. It is going from 0 to 3. What is the integration of y square? It is y cube by 3. Y cube divided by 3. Our limits have to be put 0 and 3, upper and lower. So it will be nothing but 3 cube divided by 3 minus 0 cube divided by 3. So this will be 3 square, which is nothing but 9 joules. Now comes the final answer. Here to here the work was 2. From here to here the work was 9. So it's obvious that the net work done in the entire path was 2 plus 9, which is 11 joules. That is the answer. Is that understood, everyone? How many of you got it? How to solve this? So a lot of concepts from 11th of course needed, but you can see it is useful whether it is electrostatics question, magnetism question, doesn't really matter. At the end of the day, you will need these basics. Cool? Yeah? So that was also a kind of revision of this concept of work. But we have not yet reached our point where we were talking about conservative force. So what is this conservative force that I was talking about? Now just imagine, I start moving and I come back to the same point. So my initial location is the final location. This path is called as a closed path. What is it called? It is called as a closed path. Like every day you start from the home, you go to the school, maybe you go to the tuition, maybe you go to your friend's place, you come back eventually to your home. It is a closed path. Your path might sometimes change. Maybe one day you might decide, I'm not going to my friend's house. Maybe one day you might decide, no, I'm not going to the school, I'm bunking the school. Maybe you chill out in a restaurant. Maybe one day you go visit somewhere else. Alright, but eventually you'll come back home. So that is basically a closed path. Now in this closed path, there is a force which is acting. It could be constant, variable, doesn't really matter. So that force, alright, might be changing direction. God knows what it is doing, but yes, that force is there. So if I calculate the total work in a closed path, total work in a closed path, then the manner in which I will write it down, because the work will be due to a variable force, variable displacement, variable angle, isn't it? So I have to use integration. No doubt about it. So I will put integral over here and I will put force dot displacement, but my initial and final location are the same. So when that happens, I use a special symbol which is the cyclic integral. This cyclic integral, this is called closed integral or cyclic integral, closed cyclic, whatever you want to call integral, meaning that you are coming back to the same place. Instead of putting initial and final are the same, it's just a symbolic way of saying you are coming back. For example, I introduce a function which is called sweeping, and I introduce a variable dsweep, meaning if your mom or dad will ask, hey listen, today you have to clean your room, forget sweeping, let's call it cleaning. Today you have to clean your room. Now cleaning is maybe wiping, you are arranging things, whatever. So declean means you are cleaning a small part of your room. Maybe there is a small patch somewhere in your room and you clean that small patch. So that is declean. Are you able to visualize it? I'm just introducing, just hypothetical situation this is. I am declean means I am cleaning a small patch of that room. Now if I say integral declean, it means I am cleaning small patches. There is one mark here, okay, there is something spilled here, oh that part is not supposed to be like that, I have to clean that. So I am cleaning multiple things. But when I put cyclic integral declean, that means you clean literally everything, don't even leave one single patch and you come back. So ensure that you are starting from here, you clean, and you come back and you are ensuring you are not leaving anything. So that is the meaning of this cyclic integral. You will see this even in Gauss's law, integral of flux, closed surface, alright, so many places, even in Ampere's law in magnetism, so many places you are going to encounter this symbol. Okay, is that clear? Okay, is that absolutely clear? Everyone? Okay, perfecto, okay, amazing. My name Aditya is Shreyas, Captain Shreyas, okay. Now that we understand what is the meaning of this cyclic integral, now there are two outcomes possible out of this. Behavior. What are those two outcomes? First outcome is when you come back, the outcome is zero. And this happens for forces like gravity, electric force, right? Spring force, then also your elastic forces. All these forces, if you do this integral, they always end up being zero. But it ends up as a non-zero value. In fact, you will also see buoyancy force, the fluid buoyancy is also kind of, your zero integral, which is conservative. Non-zero values come for forces like normal, tension, friction, viscous force which comes in liquids. All these are basically forces which give you a non-zero value of this, and that's why they are called as non-conservative. So you come back to the same point, you will see the total work done is not zero. Here it is going to be always zero. So they are called as conservative forces. Think of it like this. You start from a point, you are pushing an object and bringing it back to the same point. You ask friction, bro, how much work did you do? And friction bro says, bro, I did negative 50 joules. And you are wondering, what is this, macha? I came back to the same point and still friction did some negative joules of work. And then you ask friction, you question friction. Bro, I brought you back to the same point. I thought whatever positive work you do, that much negative work you will do, total work done will be zero. Friction will be saying, no, I am non-conservative. Even if you bring me back, it doesn't matter. I have lost that energy. I have not conserved the energy. I have lost that mechanical energy as heat, in friction, to sound, light, whatever, but I have lost it. So friction does not conserve that energy even when you bring it back to the same point. But on the other hand, if you take that same block and you take it up, down, left, right, this, like that, and you bring it back to the same point, and you ask gravity, bro, gravity, how much work did you do? And gravity will be like, listen, I did zero work. You brought me back to the same point. So I did equal amounts of positive and negative work. This gravity conserves energy. And that is the reason why you see, you drop an object from the top, the potential energy gets converted into kinetic energy faithfully. So that is why it is called conservative in nature. But friction might not do that. When there is frictional force, then even if you drop the block from the top, if friction is there on that plane or on that surface, it might suck out all that energy or most of it or at least little bit of it, and by the time it comes down, you might not see that much potential getting converted into kinetic. Some energy might be lost in terms of heat. That is why non-conservative. Is this distinction absolutely clear between what is conservative versus non-conservative? So forces like gravity, elastic spring, etc. These forces, right? Even when you go anywhere, it doesn't matter, and you bring it back to the same point, it will conserve the energy. Equal positives and negative works are done. So total work done in a closed path is zero. But friction, normal, tension like forces, they are not conservative. So you bring it back, no matter how, to the same point, you will see the work done will be non-zero in nature. They do not have, I would say, they do not conserve the energy, and they are not faithful towards conserving the energy. That's why the word non-conservative. Clear? Yeah, very good. Okay, perfect. So having said that, now it kind of makes sense why we spoke about Coulomb force being conservative in nature. So the work done in a closed path is always going to be zero. And there is one special property of conservative forces apart from this, yes, work done is always going to be zero. Also, the work done is independent of the path, independent of the path. First point I told was you start from a point and you come back to the same point. Initial is equal to final. The total work done is always going to be zero, okay, in a closed path. That was the first pointer I mentioned. The second pointer means, let's say somebody starts from this point and reaches this final point over here, like this. Another person starts like this and reaches the final point over here like this. Can you see the paths taken are different, but the initial location for both of them and the final location for both of them are the same. Somebody else decides, no, I'm going to take a completely different path, and that person goes like this and reaches over here. Doesn't matter what path you take, the work done in the first path will be the same as the work done in the second path, which will be the same as the work done in the third path. It is independent of the path as long as your initial locations for all the paths and the final locations for all the paths are the same. Is that clear? So this is a very important property of electric force or Coulomb force, which you will be using at many places. Okay, very interesting property. So around 2 hours class, yeah, we'll not talk about capacitance today because it's a separate thing. It's only electrostats that we are speaking about today. Great. So having said this about conservative forces, let's see if you can figure this out. Example. There is a positive charge over here. Okay. This is the first situation. Then second example, there is a negative charge over here. Then another example, there is a positive charge here. Then another example, let's say there is a negative charge here. Okay. Now I'm going to give you some situations and you're going to predict what kind of work will be done in each of these situations. Okay. What kind of work will be done in each kind of situations is what you are going to predict. Okay. So let's do this. So this is the first situation. Then this is the next situation. Then next situation. Then so in all these situations, you are going to predict whether positive work was done, negative work was done, etc. Okay. So this is the first situation, this is the second situation, this is the third situation, this is the fourth situation. Come on, let's start with the first one over here. Okay. And I'll give you more situations after this. Okay. Come on guys, predict what should be the correct answer for this particular situation. Come on, my dear warriors. First of all, in this particular situation, if I am taking, you might be wondering what am I taking? Oh, sorry, I did not mention that. You are taking another positive charge like this. Sorry, I forgot to mention that. You are taking a positive charge over here. This is another positive charge which you are taking like this, or just like this, or just like this, or just like this. Okay. So what will happen is that you will notice this positive and this positive will experience a repulsive force, okay, repulsion force like this. And at every single point, that force is perpendicular to the displacement. So whenever force is perpendicular to the displacement, cos 90 will be 0, work done will be 0. So every instant 0 work will be done. That is one story. Other story is you are coming back to the same point every single time. That means the work done anyways has to be 0. So it's a conservative force. So it's a closed path. So because it is a closed path, the total work done has to be 0. This is one method of solving it. And second method, anyways the force was perpendicular to displacement. So cos 90 was 0 always. So anyways, even if you had added, the work would have still been 0. Okay, you don't have to break your head over it. What about this situation? Now you might be wondering, sir, on this positive charge, this negative charge will give an attractive force and all of that. Yes, I agree, and the angle will change here, like this. Don't break your head. You are again coming back to the same point. So my initial and final is the same. So it is a closed path. So the moment it is a closed path, the work done has to be 0 since the force of electrostatics is conservative in nature. Since it is conservative in nature. This point is also clear, everyone, till this point? Okay. So doesn't matter now, even if I had not drawn a circle, imagine if I had drawn something else also, but I come back to the same point, the answer would have always been 0. Now let's talk about this. Here positivity is there. So you will see that these two forces will, these two charges will repel. So there is a force of obviously repulsion in this particular scenario. I am going from here to here. The force is parallel to the displacement. That means theta is acute, and for acute angles, cos of theta is always positive. That means the work done will also be positive in nature, not 0. From here to here, the electric force will do a positive work on this particular charge. Is that right? Yes. Hi Arsham. Very nice. Okay. Can you guess the answer of the last one, everyone? In the chat box right away right now. What will be the answer for the last one? I am bringing it here and then I am taking it there. You might be wondering, sir, I don't know this amount, I don't know that amount. I agree. Now, why not replace it with a convenient path? And the convenient path in this scenario will be just taking it like this. This is an alternative path with same work, with same amount of work done. And why am I saying so? Since the force of electrostatic is path independent, no matter how you take it, it is independent because it is conservative in nature. So I can take it like this, I can even take it like this, it doesn't matter. Now in that path, you will notice that this positive and negative will always attract each other like this, something like this. Yeah, there will be an attractive force. And guess what? This particular attraction would be always perpendicular to the displacement. This force of attraction is always going to be perpendicular to the displacement. That means theta is 90. That means cos 90 is 0. So always the work is 0. So the work done will be 0 in this scenario. Is that absolutely clear? So we can easily guess whether the work done is positive, negative, 0, or approx sign by looking at the diagram, just by the concept of conservative forces, independent path consideration, and also looking at the angle sometimes. Cool? Everyone till this point absolutely fine? Okay. So now I understand, sir, why you said Coulomb force is conservative in nature and what is the meaning of conservative force and how we can use it. Now what does this conservative force exactly conserve? Well, it conserves mechanical energy, and mechanical energy is a combination of two things. One is the kinetic energy, which we are already aware of, half mv square, but the second part is the potential energy. So let's talk about potential energy for a moment and then let's go to electrical potential energy. In general, potential energy, the crude definition is basically it is nothing but the stored energy. It is the stored energy with capacity of doing work. Some kind of work, and that comes due to the arrangement of that body. Arrangement also sometimes can be called as the configuration, of that system. Now what do I mean by this complex statement? Stored energy which has capacity of doing work due to the arrangement. Well, I know you might have learned about potential energy in your lower grades, but still, see, if I take a spring and I have pulled it, that pulling is that new configuration of that system because I have expanded it. That is, that extension is that new configuration or the arrangement. So I know for a fact that this spring has some spring potential energy in it. It has some spring potential energy in it, and I know that it has capacity to do work, because if I take that extended spring and I attach it to something, it will pull it and it will give it energy. It has done work on that particular object. So if I attach it to a block or something, then it moves. It starts moving, and this is the work done by the spring. It has started moving because it was pulled, and it will start pulling it. It has done some work. So it has capacity of doing work. It has stored amount of energy, and this is the pulled state or configuration. Same way, if I take a elastic rubber band, I stretch it, the stretching is the configuration, I release it, I can see it can start moving the particles around it, it has capacity to do work. Same way, if I take water and take it up on a hill and leave it, I know the water will flow down, it has potential energy stored in it, and I know this has ability to turn into work. It can push some rocks, it can push some machine to generate electricity, it can push anything, any obstacle on its way, so it has ability to do work. Okay, and it is a stored form of energy. This stored word is also important because this notion of stored can only come with faithful forces, and I cannot expect it from not so faithful forces. The faithful forces are gravity, electric, spring, elastic, buoyancy kind of forces, and the non-faithful forces are normal, tension, friction and viscous. Why am I calling them faithful versus not faithful? Simple fact, conservative, non-conservative. Just imagine, I tell, bro, friction, I will just ask you to do some work, I'm just going to move this block, okay, there, and then after some time I'm going to come back. Okay, please don't do any work. Friction will be like, sorry, I will do work, even if you move slowly, fastly, this way, that way, if you move, that's it. Even if you come back to the same place, I will do work. I will suck away all that energy. I will try to, give away that energy somewhere. So the total work done will be non-zero. That is why that word non-conservative. So it is not faithful. It cannot store energy. You cannot say to friction, bro, you moved like this. You did negative work, no? So you did negative work. You took it from me. Now give it back. Friction will be like, what nonsense? I will not give it back. That's it. Gone. It's like giving money to your friend sometimes and you never get it back. Non-conservative. But there are some friends who you give money and then when they come back after whatever their job is done, they give it back to you. That is conservative. Getting my point? So non-conservative will not give you back what you give, but conservative will give you back what you have given to them. So they are faithful versus non-faithful. So that is why you will see this word stored has so much of importance with conservative forces. You cannot use the concept of stored energy with somebody who is not faithful, like friction or viscosity or normal and tension, because they can't store, they'll just give up, they'll be like lost. It's gone, I spent that money, what are you going to ask me for? Is that making sense? Yeah, awesome. So can I then say the concept of potential energy, by the way, the symbol of potential energy is sometimes U, sometimes they also use P. This concept is associated only with conservative forces. Only with conservative forces. You cannot associate it with non-conservative forces. That is the reason why you hear words like gravitational potential energy, gravitational potential energy. You hear words like spring potential energy. You also hear words like elastic potential energy. You also hear words like electric potential energy, etc. But you will never ever hear frictional potential energy, viscous potential energy, normal potential energy, tension potential energy. Never ever will you hear such words. Is that clear, everyone? So this concept of storing is there only with conservative forces. So that is why only they have that right to associate themselves with potential energy. So all the conservative forces have an associated potential energy. So if there is a gravitational force, there will be gravitational potential energy. Magnetic force, magnetic potential energy in magnetism chapter. Spring force, spring potential energy. Elastic force, elastic potential energy. Electric force, electrical potential energy. Is that clear? Everybody? Come on, give me a thumbs up, guys. Yeah, spam. Yes, sir, we understood it till this point. Why this concept of potential energy has come. Amazing. Now, that we understand what potential energy is, let's also understand what it wants to do. So let's take an example. Say this is our earth, and then this is our block. I know it is highly exaggerated, a block can't be so big compared to the size of the earth, but just chumma for explanation's sake. So this is your earth, this is your earth, this is your block. I am giving you two situations, situation 1 versus situation 2. Situation 1 versus situation 2. This is situation number 1. This is situation number 2. Now tell me, in which situation is the, by the way, there is gravitational potential energy here. Why there is gravitational potential energy? Because this is a block and you leave it, I know it will do some work, definitely. Okay. So there is gravitational potential energy. Can you compare which situation has more potential energy? Situation 1 or situation 2? Come on, tell me in the chat box. Yes, Arsham, come on everyone. Tell me quickly. Which situation do you think has more potential energy gravity wise? Is it situation 1 or is it situation number 2? What do you think? Everybody will be like, sir, obviously, sir, I remember one formula, mgh. Oh, sir, height is there, sir, m is there, sir, g is there, sir. So, definitely, mgh, sir, option 2. Yeah, you are right. But have you ever thought why it is more? Have you ever thought why is that energy more? Obviously, potential energy of 2 is higher than potential energy of 1 gravity wise. We are talking about gravitational potential energy. Gravitational potential energy is what we are comparing over here. Yes, this is 2, which is more than 1. The reason is because it has more ability to do work. The reason is it has more capacity of doing work. And if you don't understand how to measure capacity, it's okay. Just look at their faces and ask them, are you happy or sad? So what do you mean by look at their faces? Just look at this block. Think about it, what it is experiencing. This versus this. Which block will be happier? This block which is taken up versus this block which is taken up versus this block which is down. When you take the block up, you are taking it against its will. There is gravitational pull down. This block will definitely be happier than this block. Think about it. If I had to put a smile, I would definitely put a smile on this block, and I would say this block will be sad because you have taken that block against its will, its natural tendency to come down. The tendency, the natural tendency was to come down, natural tendency to fall due to gravity, and you have taken it against that gravity. So if you know if somebody is happy or sad, that's enough to guess whether they have more or less potential energy. So everything that is sad will have higher potential energy, and everything that is happy will have lower potential energy. Simple. So you will see that every kind of system will try to go from a sad phase of life, to a happy phase of life. And when they become happy, is when they lose their potential energy. So this is what a natural process looks like. This is going to have high potential energy. This will be low potential energy. This is low potential energy. So every system always tries to lower their potential energy state. Always. And you might have heard about this in your chemistry lecture. Sir, what? In chemistry? Yes, everything that has high potential energy will try to go to low potential energy. See, even take the spring. You stretch it, it has high potential energy. Release it, it wants to go to that natural state by lowering the potential energy. You take anything, you take a elastic rubber band, you pull it, it has high energy, it is sad. You'll release it, it becomes so happy to come back to its original state, lower energy. So every system goes from high to low energy, it becomes happy. So just looking at the expression, you have to feel it, you have to feel physics, otherwise you will always be confused, then you cannot judge it. Just for an example, say I tell you, listen bro, okay, see this now, this is an example, this is a positive charge, this is a positive charge, okay, I am taking these two charges closer. If I bring them closer to each other, can you guess whether the potential energy will increase or decrease? You don't have to know any formula, doesn't matter, just can you tell me whether potential energy will increase or decrease? Just think what will happen when they come closer. There is more repulsion. You are going against their will. Think about it. There is repulsion. There is repulsion over here. There is repulsion over here. You are going against their will. So earlier they would be very happy. Now you are making them sad. So when they were far away, they would be comparatively fine. But when they are closer, definitely they are going to be sad. So definitely it has higher potential energy, whereas this has lower potential energy. So bringing them closer will increase the potential energy. Is that right? So you have to feel it. Yes, it's against its will. Similarly, if I tell you, listen, forget about charges, even magnetism we can discuss now, even magnetism. Imagine this is South Pole, this is North Pole, and let's say this is South Pole, this is also North Pole. Imagine now these two magnets, I'm bringing them closer to each other. I'm bringing them closer to each other. What do you think will happen to their potential energy of magnetism? Well, the North Pole is closer to the South Pole. We know opposite poles will attract. So now there is definitely an attractive force between them. There is an attractive force between them. So imagine when the magnets were far away, versus when the magnets are closer, there is attraction. So definitely they will be happy when they are closer, versus when they are far away, you are against their attractive force, so they will be sad. So when they are happier, that means lower potential energy. When they are sad, that means it has higher potential energy. So obviously bringing them closer will reduce their magnetic potential energy. Is it now very simple to compare the potential energies of any configuration? Just see whether they are happy or whether they are sad. Are they okay about it? Are they not okay about it comparatively? Okay, all right. RR edits to make sure that I continue teaching to all of you on the JEE English channel. That's why I'm here. Or else, what is the reason for me to be here? Okay, cool. Now, having said that, my dear students, coming back, I was telling that, you know what, this concept is also related to chemistry, and I'll tell you why. Don't have to go too much into it. So just think like this: when a system has high potential energy, natural tendency is to lower the potential energy. What happens when potential energy reduces? Think about it. You drop a block from the top, the potential converts into kinetic. Kinetic energy increases. That means every system which lowers the potential energy will indirectly be increasing the kinetic energy of the particles or the body. So if the kinetic energy of the particles or the body are increasing, that means the motion is increasing, that means the randomness is increasing, that means the entropy of the body, the system is increasing. And that is the general law of the universe which comes in thermodynamics, right? The second law of thermodynamics, which says the entropy always increases. So this was very natural. It should have happened. I would be surprised if it was the other way around. How many of you have heard about the law of entropy? Just quickly put up a heart emoji in the chat box, and I hope it has opened your eyes why this is such a natural thing. Everyone? Yeah? First PU syllabus? No, not the entire first PU, only whatever is required, man. Okay? So entropy is randomness, which is motion. So kinetic energy comes from it. And where has kinetic energy come from? From the loss of potential energy. So this is very, very natural. Very good, Vijay. Very good, very good. Hi, Ramika. Okay, perfect. Understood? Clear? I hope things are making a lot of more sense now. Okay, great. Now, I have one more problem and issue over here. And that issue is, imagine this particular block is over here. And this was your earth. And this is your block. Then my question to you is, does this block have zero potential energy? A lot of people will be like, sir, H is 0, MGH is 0, so yes, 0. That is wrong. So this block does not necessarily have zero energy. In fact, this concept of zero is little bit absurd. And energy of potential is usually relative in nature. And I'll explain you why in a bit. But also, let me explain in another way. Look at this. If I had to just remove this earth surface like this for now, and I dig a tunnel over here like this, then I know this will fall like this. So definitely it has capacity to do work. So then you will be like, yes, so potential energy is there. Isn't it amazing? So potential energy is definitely there. You can see it will fall down, just like you take water on the top of a hill, it falls down, so it has potential energy. So just that the surface was there, it was preventing it. Just like, think about it. If I tell you, listen, this pen is there right now on this book. Just because you see a flat surface does not mean this particular pen does not have potential energy. It has. This surface was preventing it. So a lot of people ask this question actually, sir, you just said everything which is having higher potential energy will naturally try to go to lower potential energy. So why doesn't that block on the top fall down? Because it wants to lower the potential energy. Why doesn't anything on the top just keep falling down? Because it will be happy. Why can't everyone just be happy? Why is everyone sad? The answer to that is, see, it is not so simple. There are things which are preventing it. Just like you might be sad now, you can be happy, you can lower your energy, but something is preventing from happening. And maybe that rock is not able to fall down because some other rock is preventing it. Maybe that book is not falling off the table and it can lie on the ground, become happy, but it is not doing that because the table is preventing it. So there is some preventive force which is coming into play, which is not letting that happen. But yes, if that preventive force was removed, it will immediately lower the energy, it will become happy. So the same way, my dear students, this was just a preventive force which was not letting that happen. So you could not sense that potential energy, but it was always there. So it can definitely fall down, it definitely had potential energy. Wow, sir, this is so cool. So sir, won't this block at the center of the planet have zero energy? Because if I leave that block at the center of the earth, then it will not move. Agree, disagree? Agree or disagree? Come on. Yes, sir, because at the center of the planet, it will have zero energy. So a lot of people think we should take the zero potential energy at the center of the planet. But here is the flaw. Even at the center of the planet, now this is Earth, but if you go to the moon, again at the center of the moon, the energy is zero, you are saying. If you go to center of the Jupiter, then energy is zero, you are saying. So for different planets, you are going at their respective centers, and then you are saying there the force is zero, that's why potential energy is zero. Feels little bit flawed, because even when you are at the center of the earth, I mean, who says the actual force is zero? There might be the force of the moon, there might be the force of the sun, there might be the force of the stars. So are you going to sit and count all the forces and be sure that the actual net force is going to be 0? Also, it has not moved, it has no capacity of doing work. It's such a headache. So finding that place where it really literally has no force acting on it, because of which it can't move, it has no ability to do work, becomes very, very difficult. So we made it very, very simple then. And we said that, listen, let this be the universe. Let this be the universe. Okay, what is this? This is our universe. This universe has countless of stars, galaxies, planets, God knows 100 different things. Okay, and you just reach on the edge of the universe. That means you are really, really far away. Don't think, sir, there will be some star, no sir, somewhere at the edge of the universe. The edge of the universe is a hypothetical concept. Okay, that means you are literally far away. So you are on the edge of the universe means you are far, far away from all the masses. At this particular point, you are far, far away from all the particles, from all the bodies, or basically matter. At such a place, the force of gravity will be definitely 0. Force of gravity will definitely be 0. Actually, not exactly 0, but it will be tending to 0. So ideally, I should use tending symbol over here, because equal to means literally equal to 0, but this will be tending to 0. And if I just come outside the universe, it's like I have crossed all the limits. The force can't feel me, I can't feel the force. So that's it. Even if I leave a block over here from the edge of the universe, just outside of it, it has no way to know what are things which are attracting it. Gone. It will not move only. It has no ability to perform work. That's it. So it has 0 potential energy. So such a location will have 0 potential energy. And this 0 potential energy is then used as my reference point to calculate potential energy at any other place. This is that place which I call it as 0, and with respect to this 0, I calculate the potential energy at any random place inside the universe. Because defining this 0 is so simple. I say when distance is infinity, r is infinity, I am very, very far away, negligible, no two force is there, no way of knowing if any planet even existed. So even if I leave that object, it won't move, it has no ability to perform any work. So 0 potential energy as the 0 point reference. Is that clear, everyone? Yes. Is that clear, everyone? Why it is called 0 reference energy? So now think about it. If I tell you, I take this block, I take it very, 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 very far. Okay, I take it really, really far. Okay, let's take it. This is our Earth. This is our Earth. This was our universe. This is very small diagram, guys, so don't worry about it. My block is here versus my block is here, or my block is, let's say, here. 3 situations: situation 1, situation 2, situation 3. I know situation 1, potential energy at infinity, that means in this particular situation, will be 0, because that is my starting point, that is my reference point, that is my starting point. Think, as it comes closer, because of the attractive force, won't it become happy a little bit? Because of coming closer, it will become even more happy, isn't it? So this system is becoming happier and happier when this block comes closer. So it should have lower potential energy. It should have lower potential energy. Oh, so here the potential energy was 0, it became lower than that. What is lower than 0? Negative. So that's why the potential energy at this place will be negative. The potential energy at this place will be even more negative. I would say more negative. More negative. Gravitational potential energy is what I'm discussing here. So this is how gravitational potential energy eventually becomes negative. You might have seen that in 11th standard. You might have been confused. Now it kind of makes sense. So negative potential energy does not mean something really scary or out of the box. It's just that you had taken the reference as 0 at infinity. So at infinity it was 0. Around me it is negative, means with respect to infinity it is less. So if I have to take that box to infinity from negative to 0, that means I have to increase the potential energy. Making sense? If I had to take this block from here to here, so from negative 5 joules, I have to take it to 0 joules. Negative 5 to 0 is extra 5 joules to be added. So I have to increase the potential energy. That's what it would mean. So it's negative with respect to infinity. Clear, everyone? Now let's talk about electrostatics and see what to do. About gravity, things were relatively simple because the forces are always attractive. The problem with charges, it could be positive and negative. Forces can be attractive or repulsive. So let's take all the possible scenarios and let's think about it. So let's say this is our positive charge. Let's say this is negative charge. Or let's take, negative charge only. And then again a positive charge. And let me define what is infinity. Okay, this is our infinity. Oh, too big, huh? Infinity. Okay. Then this guy's infinity. 3 different scenarios. Okay, these are 3 different scenarios. Okay. And all these boundaries, these are basically universe edges. This is our universe. So that means the distance becomes infinitely large, very, very far away. And at these places, you take it as 0 reference potential energy. 0 reference potential energy. Okay. Now imagine I take a positive charge and I'm placing it here, and I slowly bring that positive charge closer and closer. Okay. Here also I take a negative charge and I bring it closer and closer like this. I bring that negative charge closer and closer. Here positive with negative. I could have done the opposite also, negative with positive. That's okay. For now, let's just take this and I bring this negative charge closer and closer. Let's think what will happen in every single case. Okay. So in this scenario, positive and positive will definitely repel. Negative and negative will definitely again repel only. Positive, negative, or even if this was negative, this was positive, obviously they will attract each other. They will attract each other. Now let's think about their happiness or sadness. In this scenario, you guys think and tell me whether they will become happy or sad. Just think. These positive charges are being brought closer, they are repelling each other. So they would definitely not be very happy about it. They would be definitely sad. So this dude is going to be sad, whereas this dude, okay, maybe flat, or maybe, okay, neither happy nor sad, 0 energy. I'm out of the universe, man. If you're out of the universe, you're moksha, you're like, yeah, you're like attained like higher level of consciousness, God knows what. So you're neither happy nor sad, but you're definitely okay about it, chill dude. But when you come closer, you're sad about it. So you are being sad means higher potential energy. Higher potential energy. What is higher than 0? Because when you are outside the universe, then potential energy at infinity is 0. So what is higher than 0? Positive. So that's why you will see the potential energy is positive. Potential energy is going to be positive in value. Similarly over here, when you are infinitely far away, anyways we all know U infinity, infinite distance, the potential energy is 0. In this case, again you are coming against your repulsion, so you are definitely going to be sad. So that means higher potential energy. So that means higher than 0. So the potential energy is going to be positive. Potential energy is going to be positive in value. Whereas in this situation, it's attraction. You are going with the flow. You are going to be so happy about it as compared to this situation. So you are becoming happy. That means you are lowering your potential energy. What is lower than 0? It is negative. So potential energy is negative. So this means for repulsion, the potential energy is positive. For attraction, the potential energy is negative. Is that clear? So two positives or two negatives which will be repelling, you will see the potential energy of such a system will be positive in value, whereas positive, negative, the potential energy will be negative in value. Okay, is that clear? Pakka, everyone, about this concept of potential energy, conservative forces, more or less, positive, negative, 0 reference, etc. Now, what is the actual value, sir? Please tell me. So, if I take the electrical potential energy of 2-point charge system, you will notice first this is Q1, this is Q2. I bring these charges close enough, separate it by distance of r. Earlier they were separated by infinite distance. When their distance is infinity, the potential energy is 0. This is your 0 reference when they are very, very far away. For practical purposes, few meters, few centimeters also becomes infinity for the charges, because the forces die out very fast for electrostatics. It's only at atomic distances these charges will behave with some considerable force. So for charges, even few millimeters and meters also is good enough as infinity. Okay, the electric force is a very short range force. So in these scenarios, the forces are going to be there, and because of that forces, it will have potential energy, and that potential energy U is given by same constant, which is 1 by 4 pi epsilon naught, which is your Coulomb constant, 9 into 10 to the power 9, into charge 1, charge 2 divided by just r, no r square over here. If you want, you can also write this as Q1, Q2 by r, and instead of 1 by 4 pi epsilon naught, some people also write K, which is Coulomb constant, or C also you can write, whatever you prefer. So this or this, one and the same thing. Okay, both are same. This or this, it's one and the same formula. You can block any of this. This is the formula. Now notice how it turns out graphically. If this is my distance r and this is my energy, this is 0. If both the charges are of the same sign, positive, positive, or negative, negative, meaning they are repulsive in nature, like the one here, positive, positive, or negative, negative, then plus into plus is a plus, minus into minus is also a plus. So the energy will be positive, exactly what we predicted even without the formula. But if one of these are negative, positive into negative is a negative, exactly what we predicted, it will have negative potential energy. So the graph looks something like this. If the charges are like in nature, it will be somewhat like this. So it is positive, positive, or negative, negative. Basically, they repel each other. And this is how the graph will be. It's an asymptote. It goes like this, and almost touches there. And here it is like this. It is for either positive negative or negative positive, which means they attract. And you can see the values are on the negative side of the energy axis. Why is this graph curved? Because it is inversely proportional to R. And by the way, whenever such a graph, which is magnitude wise, if you see, it is inversely proportional to the distance, inversely proportional to that particular distance, then keep in mind one important thing, guys. Such a graph which is inversely proportional to the distance, it is always going to be a rectangular hyperbola. Rectangular hyperbola. Rectangular hyperbola. So this shape, this curve is called as a rectangular hyperbola. So you might have heard about hyperbolas. So a hyperbola is basically something like this curve here and this curve over here, this like this and this like this. If you draw tangents to it, asymptotes, they are like this. When these are perpendicular, these asymptotes, then it is called as a rectangular hyperbola. But this hyperbola, if I turn it like that, oops, this particular hyperbola which is there, if I place this curve over here, this is exactly what it is. That is the rectangular hyperbola. Okay, cool. Keep that in mind. Just remember this word. Mathematics wise, you don't have to do anything. Okay, cool. Understood? Understood, everyone? Pakka? Very nice. Very nice. Very nice. Great. So maybe let's do a simple question on this. A charge of 2 millicoulomb is taken is 10 meters away from a 3 millicoulomb charge, actually minus 3 millicoulomb charge. Both have a mass of 5 gram each. 5 gram each. Now, because the charges are opposite to each other, so that's why they will attract, and because of the attraction, you will see that they will start increasing their speeds. So when their separation is let's say let's say 10 nanometer, find the change in electrical potential energy. So let's draw the diagrams first and let's visualize. So right now we have two charges. One is positive 2 millicoulomb, the other is negative 3 millicoulomb. Their separation is really far. You can see it is almost how much meters? 10, no. Have a mass, oh, that was not given initially, sorry. No, it is given 10 meters. So that is given to be 10 meters right now. Eventually what will happen, these two masses, because of the attractive force, the distance becomes 10 nanometers, not meters. So this positive charge and negative charge have come very close. So in this process, there will be a change of potential energy. Calculate the change in the potential energy. Shall we do this? Okay. So let's focus, guys. First of all, if you calculate initial potential energy, it will be Coulomb constant Q1, Q2 divided by R. Coulomb constant is 9 into 10 to the power 9. Charge 1 is 2 millicoulomb. So 2 into 10 to the power minus 3 into 3 into 10 to the power minus 3. Whole thing divided by what is the distance? 10. So just divided by 10. This is the formula that I will be using, nothing more, nothing less. So what is this value going to be? Just check it out. Now this 9 into 2 is 18, or 2 3s are, you can say 6, okay, or 18 into 3, which is nothing but 54. Okay, so we will have 54 over here. This minus 3 and minus 3 will become minus 6. 9 and minus 6 will become plus 3. With this 10, it will become 2. So into 10 to the power 2. So essentially it will become 5400 joules. Is that right? 5400 joules is the answer. Now why is this answer so high? Don't be scared. Reason is the charge that I have taken are also very, very high in values. You'll be like, what sir? You are talking about millicoulomb. It's a small charge. Yeah, you might feel that the word milli might make you feel that it is a small charge, but actually 2 millicoulomb of charge is a tremendous high value of charge. Collecting such a charge will require special equipment. So guys, it is actually a very high value of charge. Is that absolutely clear, my dear warriors? Everyone? Yes, amazing. Now, because of which we have got a high value. If we had taken realistic charges, which is usually nanocoulombs and picocoulombs, this would be minus 6. You can immediately see this value will reduce drastically, which is more realistic. So that is why for decent distance of even few meters, the energy is so small that it is often ignored. Anyways, coming back to the point, let's talk about the final energy now. Again, same thing, 9 into 10 to the power 9 into charge 1, which is 2 into 10 to the power minus 3 into 3 into 10 to the power minus 3. The whole thing divided by, it is now what? 10 nanometers. So nano is 10 into 10 to the power minus 9. Okay, now let's see what will happen. 9 2s are 18, 18 3s are 54 again. But this time things are a little different. See this minus 3 will become minus 6. Minus 6 with minus 9 will cancel. It will become minus 3 below. So minus 3 will go on the top. It will become plus 3. Plus 3 and plus 9 will become plus 12. Oh my god, this is so huge, guys. If you want, I can write this as 5400 into 10 to the power 10 joules. Insane amount of energy has been acquired finally. But there is one small thing which we have missed, and that is the sign. So do not forget, one of the charges was negative. So initially when I had to put the charge, it was negative. So the final answer would have been actually minus 5400. Same thing over here too. This charge was negative. Do not forget that. So these energy equations are always sign sensitive. So this is also negative 5400, 10 to the power 10 joules. Now look at this number versus this number. So when you bring very close, the energy has become so high because remember, electric forces are short distance forces. They are very, very active at very short distance. So that's why it became so big. So this becomes negligible in front of it. So even if you try to find the change of energy, which is the final minus initial energy, the final will be minus 5400 into 10 to the power 10 minus, okay, minus initial, which is just 5400 joules of energy. This is like, you know what, maybe Elon Musk has, or Bill Gates, or maybe Ambani has. This is what probably I have right now. So yeah, if you ask some very rich person, or if that rich person loses 5,000 rupees, I don't think he will bother so much because he has billions of rupees in his account. So this is a very, very small or negligible amount. This is negligible amount in front of this, and that's the reason why I can just write it down as minus 5400 into 10 to the power 10 joules. That is the final answer. So the change is change is minus 5400 into 10 to the power 10 joules. Is that clear? Yes, Abhijit, I do remember you, my foundation student, definitely. Don't worry, Abhijit, I'm here. Because I want to continue on JEE English, that's why I'm here, okay? Alright, is this clear, my dear warriors? Okay, so we found out what is the change of electrical potential energy via simple formula. But, you know, this negative change also means one more thing. Since delta U is negative 5400 into 10 to the power 10 joules, I'm more interested in this negative sign. It means that the potential energy has reduced. What happens naturally when potential energy reduces? Potential energy reduces, that means it has become happy. Earlier it was sad and now it has become happy. So what will happen in this due process? It's obvious now, kinetic energy will increase. Kinetic energy will increase. That means the charges will gain speeds. And it is obvious that why they should gain speeds, because of the attractive force. So the charges will be moving towards each other. And if you ask me what is the kinetic energy, the answer will be exactly 5400 into 10 to the power 10. That's their total kinetic energy. So the kinetic energy of charge 1 and charge 2 together is exactly 5400 into 10 to the power 10 joules. This is K1 plus K2. That means this charge and this charge together will have this much energy. Is this okay? Give me a thumbs up, guys, then we'll go to the next part. All right. Now, sometimes what will happen, you might not just have two charges, you might have a collection of charges. So say for example, you have a charge here, a charge here, a charge here, and a charge here, and so on and so forth. Okay. I'm putting some random charges here and there. 4 or 5 charges. Then, when you have to find the potential energy of a system of charges, what do? Is you basically take the sum of potential energy of each pair of charges. For example, you find the potential energy between these two, whatever it is in joules, add it with these two, with these two, with these two, then with these two, then with these two, then with these two, then with these two, and then with these two, and then finally with these two. I hope I have taken all the combinations. So take all the possible combination. So if there are n number of charges, my potential energy of that system will have many pluses in between, something here, something here, something here, something here. So there will be basically NC2 number of pairs of charges, NC2 pairs. And this is a standard problem of mathematics. If there are n non-collinear points, then how many line segments can be drawn from it? So that is NC2. Okay, so you have n objects and you take it at a time, 2 at a time. So how many combinations are possible? NC2. So if there are n charges, you will get NC2 number of terms. What do I mean by it? We'll also see it via an example. All right, let's start with a triangle and then we'll go with a square. Say I tell you there is a triangle over here, equilateral. This is plus q, this is minus 2q, and let's say this is 3q. This is A, this is also A, this is also A. The question is, find the potential energy of the system. Find the potential energy of that particular system. How do we do it? It's straightforward. I'll tell you. Take 2 at a time and add them, nothing else. So the potential energy of the system will be take these two first. So Coulomb constant into Q into negative 2Q divided by A plus then these two at a time, then K into minus 2Q into 3Q divided by that A plus the third pair, which is this with this, which is KQ into 3Q divided by A. As you can see, Q, Q, A and K are common. So take all these people common, KQ square by A. And inside the brackets, whatever is not so common, like minus 2 into 3 is minus 6 and 3 into 1 is just 3. Okay, these are the numbers that I am getting. Minus 2 and minus 6 is minus 8. Minus 8 plus 3 is minus 5. So the final answer will be negative 5kQ square divided by A is the potential energy of that triangular system. Is that clear? How do we solve this? Everyone? Yeah? Similarly, let's take another example. Let's take another example, and this time we will take a square. This is Q. This is 2Q negative. This is negative. This is Q. And the side of the square is basically A. Question is the same. Question is the same. The question is find the potential energy of that particular system. Okay, so let's try and do it. Can you guess how many pairs will come? There are 4 charges. N is 4, so 4C2 is 6. Correct? So 1, 2. This 1, 2 is the second one. This third one. This fourth one. This diagonal and this diagonal. So totally 6 terms are going to come. So let's start with it. Potential energy of the system will be this with this, K, Q minus 2Q divided by A. Again, this with this is going to be the same. This with this is also going to be the same. This with this is also going to be the same. So can I just say this is going to come 4 times basically on the sides. Plus. Now let's consider the diagonals, because 4 sides are over. Q minus 2Q minus 2Q into Q, Q minus 2Q and Q minus 2. Okay, it's the same thing. So now we are just interested in the diagonals, and we both know that the diagonals are nothing but root 2 times the side length. Root 2 times the side length. Okay, fair enough. Now let's take the first diagonal, because both diagonals are different because the charges are different. So it will be K into Q divided by root 2 times of A plus K into negative 2Q into negative 2Q divided by root 2 into A. Again, Q square, K and A is common. So let's take out all these common people out. So KQ square by A, this is usual practice because then it becomes simple to solve this. Minus 2 into plus 4 is minus 8. This is just 1 by root 2. And oh, by the way, this was also minus. Negative into negative is positive. 2 2s are 4. So this will become 4 by root 2. This will become 4 by root 2. Okay, so what will I get? KQ square divided by A. 4 plus 1 is 5. So 5 by root 2 minus 8. You can leave it like this, or if you want to rationalize and all that, it is also okay. But yeah, this is the answer. Final potential energy of the system is KQ square by 5 by root 2 minus 8. Cool? Understood? Pakka? Amazing, 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 amazing. Very good, very good. Now that we understand how to calculate the potential energy of the system, okay, we know how to calculate potential energy of the system. This can be also used for calculating force, or from force you can go to energy. So let's come to that part, which is usually the hard part, and that will cover many of your doubts. Okay, I'll give you an example. Imagine there is this mass and I take it up like this. I'm taking it up like this. In this process, I know my potential energy will increase. My potential energy will increase. Gravity will act down. Gravity will act down. Correct? And this will be your force of gravity. Whereas because I'm pulling it up, my force, my pulling force is going to be opposite of gravity, otherwise it will not come up. So let us say I do this process very, very slowly. I'm doing this process very, very slow and steadily. So when I do this slow, that means kinetic energy is basically negligible or exactly zero. So first of all, in this process, my potential energy is going to be, example, say plus 15 joules. Okay, just for example. So then if I ask you, what is the work done by the pull, by that external pull, then you'll start to think, how did the energy of this mass increase? You'll start questioning. The energy increased because it went up. Why did it go up? Because of the pull. Oh, so I pulled. So I was applying a force. Oh, so I was giving my energy to increase its potential energy. So whatever work I did in pulling has gone in potential. Are you sure it did not go anywhere else? Wait a minute. It could have gone in the speed, that means kinetic energy, but I moved it very slowly. So that means all of the work, whatever I did, would have gone completely into the potential energy. So the work done by the pulling force is also 15 joules. I did 15 joules of work that completely went in increasing the potential energy. But now there is another aspect. Sir, there is gravity also. Sir, there is gravity also. అర్థమవుతుంది ఎల్కలా ప్రవీణ్? ఓకే, ఎస్, మీరు ఎలా ఉన్నారు? ఆల్ ఫైన్, బాగుంది. ఎస్, ఓకే. సో వాట్ అబౌట్ గ్రావిటీ నౌ? గ్రావిటీ, వర్క్ డన్ బై gravity. Think about it. Gravity is acting down, displacement is up, so it will do definitely negative work because force and displacement opposite, meaning that angle is 180 degree, and whenever you take cos of a 180 degree angle, it is negative value. So even by the definition of the work, it is negative, and when they are opposite anyways, it has to be negative, so it will do negative work. But how much negative work? It will exactly do that much negative work as much as the potential energy has increased, meaning minus 15 joules. What this means is the external force did 15 joules work to lift and increase its potential energy by 15 joules. There was no loss, and gravity took out 15 joules, and because it is took out, that means negative, and stored it faithfully. So don't get scared by gravity doing negative work. We don't have to worry about gravity. It's a conservative force. So it sucked out that energy out of me, but it has faithfully kept it in that system as potential energy. That's why whatever you give is whatever gravity sucked, and it has been stored. Imagine this was something like normal friction, etc. You will do 15. This will not do 15, that normal or friction or non-conservative force. It will take more only, or it will suck out some energy, and what you will be left in increasing potential energy will be nothing, or maybe even smaller. So if it was not for gravity, which is a conservative force, these numbers wouldn't have matched. What you do, what it takes, what is changing in energy, no. So that's why you never talk about change in energy for friction, normal, tension, non-conservative forces. These are faithful numbers. The signs are irrelevant now. Just the numbers, if you consider, it makes sense why they are matching. They are conserved. The sign of negative gravity just tells you that it is sucking out that energy and storing it. What happens in the exact reverse process? If I take this block and if I slowly bring it down, just imagine now instead of going up, if I slowly bring it down. Now if I bring it down in this particular process, the potential energy decreases. Potential energy decreases, but I am doing it slowly. That means the kinetic energy is negligible. So in that situation, my change in the gravitational potential energy will be negative 15. Change in the gravitational potential energy will be negative 15. Yes, it has reduced. Because I'm slowly lowering it up, I'm still pulling it up only. Gravitational force is still down. Because if I don't pull it up, it will accelerate and it will fall down. So I'm holding it and releasing it slowly. It's like I'm holding something and I'm slowly keeping it on the table. Okay. So now my pulling force will do exactly negative 15 joules of work. Why? Displacement is down, force is up. When force and displacement are up, the work done is negative. And lastly, the work done by my gravitational force is going to be plus 15 joules because force and displacement are in the same direction. These numbers will still match. In this context, it means my gravity provided that energy, and what happened when it provided that energy of 15 joules? The potential energy reduced. And where was it taken? It was stored, or not stored, it was taken by my pulling force. So when I was holding it and slowly lowering, I am sucking away the potential energy within myself. So that's why that negative sign. But important point is these numbers match. Now, if I had to summarize this, not just for gravity but for anything, then I would write it like this. So when an external force does work on a system with potential energy, that is conservative forces, then I can always say whatever is the value of delta U, whatever is the value of the change in the potential energy, will always be the work done by the external force. So it will always be the work done by the external force, but it will also be the negative of the work done by those conservative forces. It will also be negative of the work done by the conservative forces. This is a very, very important line. Okay, very, very important line. Now from this line only you get another interesting thing, and that is, now for small changes, what happens is this delta U will become, it's not a big change, it's a small change, it will become du. And this work done will also become very, very small. So it will become minus dw conservative. I'm not interested right now in the external, I'm just focusing on the conservative aspect. So what happens now, this work done is nothing but force into displacement, but since this is a small work, this will be that force at that instant, conservative, into that small displacement. Let's say I call it dr or ds, whatever you want to call it. This is a small displacement. This is small displacement. Small displacement. This is a small displacement. This is the force at that moment, making sure the work happens. You move this around and you will see the work done by that conservative force will be nothing but minus du by dr. This is also a very famous formula which you would have encountered back in your 11th grade. And this is also true for electrostatics. So the electric force will be negative rate of change of potential energy. So this is true for, in fact, all the conservative forces. So example, I can say my electric force is nothing but negative of the rate of change of electrical potential energy with respect to r, which is nothing but distance. Now what happens is, usually you don't like to write this big statement. Whenever rate of change of some quantity is there with respect to distance, the substitute phrase for that is gradient, is the gradient of electrical potential energy. So instead of saying rate of change of with respect to distance, you use the word gradient. It is the same thing. So you might hear the word gradient. So whenever gradient is there, it is always derivative with respect to some displacement quantity or position quantity. Is that clear how this has come? Okay, how electric force is the rate of change of potential energy with respect to distance, and delta U is external work done, which is also negative of work done by conservative force. So let's take some examples to understand this. Okay, imagine there is a positive charge, imagine there is a negative charge. Somehow, for some reason, I'm bringing it closer. So in this process, can you guys quickly tell me what will happen to delta U? Will it be negative or will it be positive? First, quickly tell me that. Positive charge and negative charge, I'm bringing them closer. Hi, good evening, Silver Boy. Delta U Payal is the change of potential energy. This over here is the change of potential energy. So just imagine this. Maybe you had some system. It was initially like this. So now you have changed the configuration, you have changed the location of the particles. So in this process, U will change. If this was U initial, if this was U final, delta U will be U final minus U initial. That is the meaning of change of potential energy. And why this has happened? Because some external force was there or whatever, and there would be some internal forces which are the conservative forces. Okay, so coming back to this question, once this comes closer, what is happening? There is attraction between them, do not forget. So definitely there is attraction, and once there is attraction, they would love to come together, and as they come closer, they will become more happier, versus when they were far away, they would definitely be sad. So because they are coming closer, so definitely there will be lower potential energy, and lower potential energy means delta U will be negative. So if I say, is that clear why it is negative? Because they are attractive in nature, so they come closer, so they become happy. Happy means, yes, I am lowering my potential energy. Delta U will be negative, let's say it is minus 20 joules. Now can you guess what will be work done by electric force? What is the work done by electric force? Think about it. Electric force is a conservative force, and we all know negative of the conservative work is always going to be delta U. So therefore the work done by electric force will be negative of delta U. Delta U itself is minus 20. So therefore the work done by electric force will be positive 20 joules. Will be positive 20 joules. Clear? This is how you can calculate energy changes, work done, etc. in electrical systems. In those electrical systems. Now, one such example could be, take this or even take this. Okay, let's take this only. We just had calculated this some time back. Okay, we just calculated this. Now, Oh, I can't move this. Okay, for some reason I can't move this. Now we had calculated the potential energy of the system, which was minus 5kq square by A. Let's say I take this triangle and double the size. Then can you find, then in this scenario, can you find how much energy will change and what is the work done by those electrical forces? This kind of question is also very, very common. What is the change in the energy and what is the work done? There will be some electrical forces involved here. How much work will those electrical forces do? You don't have to be scared, sir, will I have to integrate? No, you just have to calculate delta U. Whatever is delta U, the negative of that will be electrical's work. Okay. Now, what you need to do, first delta U. How do I calculate delta U? We know when the distance was A, the initial potential energy will be exactly this, minus 5k q square divided by A. What will happen if you double the size? Instead of A, you will have to use 2A, that's it, right? Nothing else. The whole derivation will be the same. So the final energy is obviously going to be minus 5q square. Just instead of A, you are just going to put 2A. That's all. That's the difference. So now, if you calculate delta U, which is final minus initial, final is minus 5kq square by A minus 5k q square, sorry, this was 2A by A. So as you can see, minus minus will become plus. So it will become 5k q square divided by A minus 5k q square divided by A, and this 2 over here. Now this is, if this is x, this is x by 2. X minus x by 2 is x by 2. So this will become 5k q square divided by A. That is your delta U. Very simple to find delta U. So now the last part is to figure out is how much is the work done by electric force. We know negative of the work done by electric force is delta U. So therefore work done by the electric force, that negative sign I take it here, and whatever is delta U, I'll just put it over here. Why did that 2 not come? So this will be nothing but minus 5k q square divided by 2A. So electric force has done a negative amount of work. Simple. Clear? How to calculate work done by electric force, how to calculate work done by external force, how to find change in potential energy, and what is the meaning of potential energy in electrostatics. Okay, everything I have explained it to you over here. Great. Amazing. Cool. Shall we go ahead, my dear warriors? Pakka? Okay. Now, 2 more concepts which will probably close most of your misconceptions or backlogs now, is the concept of field and concept of potential. Simply put, if you have 2 charges and there is a force between them, between 2 charges, they will also have potential energy between them. This will be always force between charges, potential energy of a pair of charge, Now you take that force and you divide it by a single charge, by one of the charges. In that pair of charges, you divide it by one of the charges over there. Then what you get is this concept of field and potential. What you get over here is nothing but electric field field, and what you get over here is nothing but electric potential. Now you might be wondering, sir, which charge do I exactly divide it with? Okay, I'll help you out with that. Let's say this is a charge Q. The other charge has to be necessarily a unit test positive charge, or forget unit, I would say infinitely small charge. So this charge Q has to be very, very small and it has to be positive. Such a charge is always called as a test charge. What is it called? It is always called as a test charge. It is always called as a test charge. This one of the charge is always going to be the test charge, because you cannot divide it with any other charge. So if just imagine the force between the two charges was K, charge 1, charge 2 divided by R square. The second charge will be Q, divided with one of those charges. But which one? The test charge necessarily. So if I divide with Q, Q will get cancelled. So what am I left with? I am left with KQ divided by R square. That is exactly your electric field. That is basically your electric field. You do not have two charges in the numerator, you just have one single charge. So you are calculating how much is the force per unit test charge. That is called as the electric field. You might be wondering why this charge has to be small. There is a simple explanation for that. If this charge is even decently big, then it will apply a force on this guy and this charge will begin to move. And once this begins to move, you are changing the whole dynamics. I don't want anything to move. I want everything to stay as it is. This testing charge should not affect the original system. Like for example, you go for a blood test. Imagine the nurse puts one big injection and sucks out 5 liters of blood from your body to test your blood type. You will die. So to test somebody, you cannot take out or you cannot affect that entire body. When you are trying to measure the voltage in one socket, you put a voltmeter and you realize the moment you put the voltmeter, the entire house burns down or all the appliances stop working. Then what are you testing? Right? So when you test something, it should not affect the original system. So that's why you take a very, very infinitely small test charge. Got it? So that is the reason why we divided with that infinitely small test charge value, and that's how I get the electric field. Same way over here as well, potential energy is nothing but KQ divided by R into small q divided by one of the charge, which is the test charge, which is small q. What am I left with? I am left with just KQ divided by R. This is called electric potential. So it is the potential energy per unit charge. The potential energy per unit charge. Okay. Now you might be wondering what is field and potential, not by formula. Likewise, I will explain you that in a bit. But before that, what would be the unit of electric field? You can see on the top you have force, on the bottom you have charge. So it will be obviously Newton per Coulomb. Similarly, what about electric potential? On the top you have energy and at the bottom you have charge, which is again Coulomb. So this will be nothing but joules per Coulomb, and 1 joule per Coulomb is also called as a voltage potential. Okay, so a joule per Coulomb of energy is called as a volt, and a Newton per Coulomb is not having any name, you just leave it as Newton per Coulomb. Okay, so that is the unit of electric field. One last thing, just like force is a vector, even electric field is a vector quantity, whereas electric potential, this being a scalar, this is also a scalar quantity. This is also a scalar quantity. So electric field is a vector, electric potential is a scalar quantity. Now what does this potential and field mean truly? I'll explain it. See, imagine this charge is there. Okay, this charge is there, q. Now there is another charge, small q. Because there is some distance between them, 100% there is a force. This charge will also apply a force on this charge F. Now the real question comes. How did this charge know how much force to apply on this charge? Or how did this charge know that this charge was here and I should experience this much force? How did this charge know I should experience this force in this direction? So think about it. Even before this happened, so this was after, when there was nothing present, nothing around this charge, even before this came. So nothing before the charge Q came. So this charge is quietly waiting for its turn outside the universe. It's outside the universe. It doesn't have any awareness that this charge is there. This charge also does not know this charge is there. It's like there is a very strict teacher and this student is outside the classroom or outside the school. So the teacher is not aware of what this mischievous kid is going to do later on. So this mischievous kid comes inside the classroom. The moment the mischievous kid comes, the teacher becomes alert and, oh, you are that kid. The kid is, oh, this is the teacher. And they both start quarreling, or the teacher starts scolding the kid and the kid starts doing some mischief, whatever interaction they have. Same way, this charge, the moment it enters here inside the universe, then it understands that, oh, I need to experience this force. What made it realize that something was there even when this charge was not there? And that something which was present around this charge, there was something which was present around this charge, but it was not a force. It was not a force. What was it? Was the field. What was there was the potential. Potential was there, field was there, but force was not there. So at this place, you can say, yep, there was field. There was field over here. 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 This field is going to be very, very strong when you come close, and as you go slightly far away, this field is going to reduce. So what was present at this moment is the field or even the potential, but not the energy and not the force, because force has to be applied on some matter, on some body. Potential energy will be possessed by a body. Right now there is nothing, it's space. So how can it experience force? So it has ability to gain energy, so it has potential, but not the energy. Just like you have potential to crack JEE, but when you crack JEE, when you get a JEE Advanced score, that's when you will, be eligible for counseling and blah, blah, blah. So then you have potential energy. So right now you have potential. When you crack the JEE Advanced exam, you will have potential energy. Right now, there is nothing over here. There is no mark sheet. There is no result. So, it's field. But when you get the result, when you get the mark sheet, that's when you have the force. Think of it like that. That is the difference between force and field, or potential energy and potential. Am I absolutely clear? I hope this conceptually you are understanding it. Yeah? Okay. Perfect. Right? So that is force and field and potential energy and potential. So I can say that electric field is electric force per infinitely small positive test charge. So electric field is, simply put, force divided by charge, limit q tends to 0. Like I said, it is vector quantity. Also, the unit, right now you are saying it is Newton per Coulomb. Later on you will also see there is one more unit which is called volt per meter. That is also fine. Alright, so later on you will see why it comes. But yeah, for now this much is okay. So this is the true way in which you write the definition of electric field, which is force per unit charge. Now if you happen to have a point charge for a point charge, that means this is my charge and I am at a distance r from it, the electric field is given by kq divided by r square. Kq divided by r square, just like what we did over here. Kq divided by r square, because q will get anyways cancelled. Is that okay? So that is the electric field magnitude of a point charge. Now, if you happen to take a positive charge versus if you take a negative charge, you will start seeing some interesting discoveries. First, you will see, because of a positive charge, if you take any other positive test charge, it will experience repulsion. So the field direction, this is a vector quantity, will be same as the force. The force will be always repulsive on a positive test charge. So that's why you will see the force will always be away from the positive charge. That means the field will also be always away from this positive charge. Whereas for a negative charge, if you bring a positive charge around it, which is a testing charge, it will always attract it. So you will see for a negative charge, the electric field will always come radially inwards. For that negative charge. Is that clear why this happens? So for a positive charge, the electric field is radially out. For a negative charge, the electric field is radially in, because of the definition of the electric field, how it is being made. Cool? Till this point, absolutely fine, everyone? Amazing, amazing, amazing. Now, how do I write down electric potential? How do I write down electric potential? Is, you can write it as potential energy per unit charge, where that unit positive charge is tending to 0. That's one way of writing, but the formal definition is not like that. It is basically defined as the work done to bring an infinitely small test positive charge from infinity to the point where potential is to be found. So say for example, just like we did it for here, say we have some system, okay, doesn't matter what that system is. That system can have maybe positive, negative, positive, God knows, some charges are there. And what you do now, you draw the boundary of the universe. This is infinity. You bring a small charge which is tending to 0 from infinity to a point where you want to find the potential. So this is the point where I want to find the potential, and the potential at that particular point is V. So that V is nothing but whatever work you did in bringing that charge. So work done in bringing the charge from infinity to that particular point divided by that small charge. But that small charge has to be very, very small. So that's why I will put limit q tends to 0. So that is the true meaning of potential. This is the correct way of defining potential. Is the work done to bring a small positive charge from infinity to a point. Okay, like I have explained before, this is obviously scalar quantity and the unit is joule per coulomb, which is called as a volt. Now if you take a point charge, now for a point charge, what will happen? This is point charge. This was not a point charge, this is some random thing. That was the definition. The electric potential at that point, remember it is directionless, it's a scalar quantity, will simply be kq divided by r, just like I had explained it over here. It will just be kq divided by r potential, because qq anyways will get cancelled. Okay, so that's the formula for electric potential due to a point charge. This was the formula for electric field due to a point charge. Now, is there something very similar to electric field lines that we draw? Yes. So I'll tell you what. If you take this particular charge and you mark all the points which has the same potential around it, you will see all the points which are at the same distance will have same value of potential. So you can say all these points have same potential energy because they are at the same distance r from it. You change the distance a little bit, then all those points again on that circle will have same potential energy or same potential. Then again you move away a little bit, you will find again there will be a set of points which will have same potential in a circular form. So guys, these lines are called equipotential lines. Equipotential lines. What are they called? Equipotential lines. So all these points have same potential V1. All these points have same potential V2. All these points have same potential V3. So that's what equipotential lines are. So if you stand anywhere on an equipotential line, the potential is the same. Okay, voltage is the same. That's the meaning of it. Why is it scalar quantity but the flow of electric charges has direction? There are two different things, Payal. Electric potential is just how much energy was required, work was done per unit charge. So work is a scalar, this is a scalar, so this also ends up being a scalar. It has no directional meaning associated with it. There is nothing like what is the electric potential in this direction or that direction. The value of potential, even if it is 10 volts minus 100 volts, it has no sense of direction. So it does not even follow the rules of vector addition. So it is purely scalar quantity. But flow of charges, that is basically current. Now current has direction, but it is still a scalar even though it has direction, because it does not follow the rules of vector addition. Okay, so just because something has direction does not mean it is necessarily a vector quantity. Like, you know, they say even time has a direction. Time has a direction in the fourth dimension. It goes from the past tense to the present tense to the future tense. But still it is a scalar quantity because it does not follow the rules of vector addition. So current also is a quantity with direction but does not obey the rules. So disqualified from being a vector. That's the reason for it. Okay. Alright. Now you might be wondering, sir, just some time back you told force is related to energy. So then you said, okay, but if you divide force with charge, you get field. You divide energy with charge, you get potential. So if force and energy are related, it's quite likely field and potential are also related. And the answer is a big yes, and that's what I want you to see. Observe. Force is nothing but negative du by dr, isn't it? Now what I do, I take this force and divide it with a small charge, and then here also I'll take negative du and I then divide it with a small charge. I also say this charge is really small. I put limit also on both sides. Quickly I realize what this limit is doing. Force per charge very small. This is nothing but electric field. Okay. I realize energy per unit charge is nothing but potential. So this will become minus dV and this dr will remain as it is. So this is also true if this is true. So this becomes my new relationship between field and potential. So I can now say that electric field is this negative and d by dr, remember rate of change with respect to distance is called gradient, is negative gradient of potential. Is negative gradient of potential. This is a very important discovery, very important formula which you should definitely know. So electric field is minus dV by dr. If you instead of field you use force, it will be negative du by dr, one and the same thing. Now this has many implications. See, if we have an electric field line, this is nothing but electric field. Then always remember that the electric field, what this statement says, is negative gradient of potential means wherever the potential reduces, that's where the electric field is going to be pointed. Gradient means change with the distance. So I move and I find my potential changes, but it changes negatively. That means it reduces. That's where my field would be. And this is true even for gravity. If there is a hill, wherever the potential, gravitational potential energy reduces, that's where you will see the forces will be directed towards. And the river exactly finds that path where slowly it can lower its potential energy from the top of a hill. Same way over here also the electric field will always go from high potential energy, high potential to low potential. Remember, it has to become happy. Low potential means it is happy, high potential means it is sad, and the field is always going to push it towards the lower potential. This is always going to be true. So also if you have some equipotential lines, let's say this is V1, V2, V3, you will notice my electric field lines everywhere will be perpendicular to it. Everywhere will be perpendicular to it, something like this. Everywhere will be perpendicular to it because it has to go in the direction of lowering potential energy. It cannot go in some random direction. If it misses 90 degree, it is then not going towards the lower potential energy. It will go to the steepest gradient, steepest slope possible in the lower potential. So if the field is going like this, it then means my potential 1 is less than potential 2 and potential 2 is less than potential 3 because it has to go towards lower potential. So this is what that symbolically or graphically it means. Okay, so this was your equation, mathematical, and this was your diagram, or I can say comparison or how the field looks with respect to potential. Okay, cool. So did you now guys get an idea of what force, field, potential energy and potential is in electrostatics? Yes or no? Are you getting an idea of it? Yeah. So this should be a good start to cover your backlogs and complete this chapter of electrostatics. Cool. So if you are interested in completing not just this chapter but also the other chapters, because now the chapters are going on in full swing in our Lakshya batch. Remember, the link for joining the Lakshya batch is there in the description box over here. So, and this is in pure English. Okay, so make sure you are a part of it. The entire schedule, everything is there, all the details for a very affordable pricing. Okay, the batch has already started, but I am conducting this class because many kids realize late, and we have taken almost some 15-16 lectures I guess for just this particular chapter. So a lot of people needed that head start. So I have covered the 11th standard basics along with 12th for your electrostatics chapter. Now if you watch these lectures, it will be very easy for you to understand. Cool. So do this guys, and I would love to see you all in this particular Lakshya batch for pure English preparation. Okay, in pure English preparation. Thank you. Thank you. Okay, have a great time. Have a wonderful evening and have your dinner now. Take care. This was Captain Shreyas signing off. Bye bye. Take care.